Um, so hopefully you'll turn in your project proposals. These proposals were meant to be short. If you realize 100 to 200 words, some of you said you wanted to write more, and I'll try and read more as needed. The point of this is so you've picked out some topic that you're now interested in. And so now when you're looking at things in class, you can kind of have in your mind, is this a useful thing to be considering for my project, right? You know, with 100, 200 words, I don't expect you've got it all laid out at this point, and since you haven't taken most of the class, I should be able to expect that anyway. So kind of, now you have your project, you know, keep these things in mind. We'll try and get feedback back to you, you know, as we can, probably in the next week or so. Yes. But all right. So also I posted homework 2, assignment 2. It's due February 17th, so you've got like 2.5 weeks, so it should be plenty of time. Last week was the last thing that you will need to do that homework assignment, so you can get started on that now. As advertised, it's going to be kind of working through the previous 3 lectures. You're going to be taking some documents that we provided for you. We've tried to put them in a nicer format so you don't have to deal with too much of the dealing with the different types of characters yourself if you're not used to it. And then you're going to be creating the shingles, or the K-grams, or something that's called shingles, looking at the Jaccard distance with them, doing the min-hashing with the version of them, and then calculate the probability for doing the LSH. To actually do the LSH, it would, you know, to get to a range where it's feasible, you need much larger data sets. And it just kind of becomes, you spend more of the time working with the data sets and that sort of issues than you do exploring the technique. So I just have you work through some of the probabilities. Okay, so start working on that. Hopefully it's not too hard but you will, again, like the first one, if you're not used to using kind of a language like Python with some data structures, it might take a little bit longer. So make sure if you're not familiar with that sort of thing, you don't wait till the last minute. Okay, and post questions on the discussion board or office hours or TA hours and so forth. All right, so the lecture for today is going to be on distances, and probably most of you know what a distance is. You know, so it's some sort of function. We'll call it uppercase D, and it goes between. So it's a bivariate function. It goes between two objects from the same set X here, and goes to R plus. So this usually is the real numbers that are non-negative. There are different ways of writing that. So for example, D, you could say two objects A and B goes to some value between 0 and usually infinity. There are some cases where it has a more restricted range, like between 0 and 1. Right? So the Jaccard distance we talked about has a restricted range here, but this is more general. And so, you know, most of you probably have heard distances. So why are we going to talk about distances in class? Well, there are a few there are a few takeaways. What are nice properties that a distance should have? And in particular, the main thing we'll look at is if a distance is called a metric, and what that means. And then we'll look at things later in class where you can use basically any distance you want often, but as long as it's a metric. So it's a very kind of general but powerful approach. Kind of one of the other things to do is list of some distances, and kind of the point to drive, I'll try and drive home here, is that often in the data mining problem, at some point you're going to need to use some sort of distance to measure, so distance, the larger the values, the further things are apart. But the choice of what distance to use is a choice. And that's a modeling choice, and which one you choose means different things for your problem. And some will have nice algorithmic properties as well, and efficiency properties. Others have nice geometric properties that we'll talk later about in class. Others have nice mathematical properties. They make kind of certain algorithms work nicer. But this is a choice. We'll see some of the advantages in some, but sometimes there's not one that's necessarily better than the other one. So you'll just have to choose, and this goes into the modeling. So I want to kind of go through some of these and give you a taste of what the differences could be, so you realize that, so that when you're doing stuff, that you have a choice here. And so then, so then finally, part of this list and part of this nice property is that some very reasonable distances will have unexpected properties. Meaning that they will seem very reasonable, hopefully, when I describe them. They're actually very useful in various situations, but they don't satisfy these properties, which I call metric. And so, if you haven't seen that before, these might seem strange, but they can still be very useful. Okay, so before we get going, so who here knows what a metric is? Yeah, and who doesn't know what a metric is? Okay, and who? Okay, 80% of you did not raise your hand. So I mean, usually it's like at least 50% of people, a binary question will raise their hand, but that was not good. So it's no, if you don't know what it is, it's fine. I'm going to explain it anyways, right? So I just want to know, because I feel like I want to make sure I'm teaching the right stuff. Okay, so who thinks they could explain a metric to me, and who thinks they could not explain a metric? Who still didn't raise their hand? Okay. And who still didn't raise their hand? A few of you haven't raised your hand yet. Okay. I'll have to let this one go. But all right. It's a good thing I didn't have a. Right. We'll have to figure out some other way to engage you guys. Okay. So a metric is a distance function, which is one of these things that has 3 or 4, depending on how you group them, has 3 or 4 additional properties. We'll write out 4 of them. Sometimes one of them is grouped in with another one. The first one is that D. Let me be consistent here. I'll sometimes use D as the dimension of something, the lowercase d. So DAB. This has to be greater or equal to 0. Right, so that was kind of in my definition. So it mapped to these ranges that are greater or equal than 0. So this one is pretty much always going to be whole. Maybe there are some cases where it doesn't, but those would be fairly strange. So it would be like the non-negativity. So this one seems reasonable. Each of these individually should seem very reasonable, right? Second one is that D of AB is equal to 0 if and only if, that's IFF is if and only if, A equals B. That means the implication goes both ways. So if it's equal to 0, then A must be exactly equal to B. If A is exactly equal to B, then the distance must be 0. Right? So this seems reasonable. So the third one is d of AB is equal to d of BA. So this is symmetry. It means that if the straight line from here to the back of the room, some point over there is what would be like 25 meters, then going the other way is also 25 meters, right? Seems reasonable. Some things where this isn't true, that might seem strange, but still very useful. And then the fourth one is that d of AB is less than or equal to d of AC plus d of CB. So this is the triangle inequality. Right? So this is basically saying that if I have 3 points, A, B, and C, so if I took a straight line from A to B, this should be faster than if I took a detour up to C and then down to B, or at least no slower than if I went up to C and then down to B. And this is the triangle and the triangle inequality. Okay? So this seems like a reasonable property for distance to have. Okay, so usually when we think about distances, we're usually thinking about the Euclidean distance, right? So I drew these points, and by drawing them on the plane, they essentially have x and y coordinates. And then we think of distance as this straight line distance, right? So, but distance are much more general objects than that, right? And so they don't have to be points as the input, and even if they are points as the input, we don't have to use this straight line distance between them. Okay, so just before I start talking about some distances themselves and their properties, let me just mention that if you have M1, M3, and M4, then this is not, so these four properties are if something is a metric. If I have just these three properties, so I'm missing M2, that it's only 0 if and only if A is equal to B, then this is what's called a pseudometric. And so if I only have M1, M2, and M4, so again I have the triangle inequality and greater than 0, but I don't have symmetry, right? So I don't have the symmetry property, then this is what's called a quasi-metric. Okay, and so metric and quasi are both words meaning almost but not quite, right? But they're different almost but not quite in an arbitrary way. That one left out M2, one left out M3. Okay. I don't know why one is called pseudo, the other quasi, and vice versa. I probably have mixed them up at some point. Okay, so we'll see examples of some very useful distances which are as a pseudometric and a quasi-metric. Okay. Okay, so keep these in mind. All right, so the first class of distances we'll go to are going to be these LP distances. Okay, so LP distances is P now is some value, usually, there's, maybe the right way to write it is like this, and then there are special cases for 0 and for infinity. So I'll explain those. But P is going to be a value, and in particular, L2 is going to be equal to the Euclidean distance. Right? So the general form for this, and we'll call this dP between A and B. And this is going to be when both A and B are going to be vectors in RD. Okay, so when I write something as an RD, and this is a blackboard bold, or in this case, a Microsoft Surface bold. I was not paid to say that. Then it means that I can write A as A1, A2, AD. So it's a vector, meaning, again, remember the ordering of these, the location matters with D elements in it. And so then this distance is defined as the sum goes from I equals 1 to D of AI minus BI, this to the, so the absolute value between those to the power P, and then this whole expression to the 1 over P. Right, so it's useful. Why am I taking to the power P and then 1 over P? It's a good sanity check is that the units are the original units. I take the unit to the pth power, and then I sum them up, same units, and then I take them to the 1 over pth power, and I get back the original units. So this is the LP distance, and the L2 would mean that this is squared, and then 1 over 2 is a square root, right? So this was the Euclidean distance I've talked about before. That's the straight line distance that we're used to seeing. Okay, and so the L2 distance, this is a metric, and so just before we move on, let's just do a sanity check that satisfies these 4 properties up here, right? So so let me write down just the L2 distance. Is this behind me? All right, I'll move it a second. Right, so that's the L2 distance, and often, yeah, one more thing, this is often written as A minus B P, so this is A minus B 2. So and there's some properties that it's the norm of the associated vector, and I'll mention that in a second. But let's check that that this is indeed a metric here. Okay, so I've squared every element, or more formally, I took the absolute value and squared it, and so each of these has to be greater or equal than 0, and then I add them up, and this cannot change the sign, right? So it has to be greater than 0. See, it can only be 0 if all the things are identical, right? This operator does not change whether or not it's 0. And otherwise, I'm adding up some quantities. And so if I add them, if they're each individually greater, they can only be less than 0 if any one of them is less than 0. Or it can only be, so all of these are going to be positive or equal to 0. So they can only be all 0 if each of the elements of the vectors are identical. Otherwise, I'm going to add some term that's greater than 0, and then I can never get rid of it. Okay, so that's the second one. The third one is the symmetry. Yeah, so the absolute value inside of here makes this this function symmetric, right, for each of the coordinates. And the triangle inequality. I could write down a proof, but so for the Euclidean distance, the proof is basically in the picture, right? If you take a detour to C, that's going to be longer than taking a straight line. This satisfies the triangle inequality for P. So the LP distances are a metric. So the triangle inequality holds, M4 holds for, this is true for P greater or equal to 1. It's less than 1. I think you messed up some norm properties. I think it's no longer a metric. But most people, there are other reasons where we'll want to use something less than 1, and one will have properties that the unit ball is convex, and this will be nice. So you typically don't use p less than 1. Sometimes you want p equals 0, which is kind of a special case that I'll mention soon. But that's often hard to work with other than just calculating it on a term-by-term basis. Okay. So what are properties? So this is the L2 distance here. What are properties of, let's talk about some of the other kind of important elements of your other LP distances. First of all, did anyone not believe any aspects that L2 is a metric? This is kind of the canonical thing. All those quantities make sense, right? So the L1 distance, so this people often think of as this is often called the Manhattan distance. But for, the reason for that is it's going to be like if you're standing on one street corner and you want to go to another street corner, you have to go up so many streets and then over to so many other streets. And you can't walk through buildings. So kind of this is similar to, when a city's laid out on a grid, it works. So you can call it, you can think of it as the Salt Lake City distance instead, since we're in Utah. Works just as well. So this was d1 of A and B, often written as A minus B1, and it's just the sum of the absolute values of all of the coordinates. So that the taking to the power of 1 over p on the outside, well, that becomes taking to the power 1, which doesn't do anything. So I'm just summing the absolute values of the coordinates. Right, so if I'm walking on, I've got this nice grid here from point A to point B, then it's this distance plus this distance. Right? So that's why it's called the Manhattan or the Salt Lake City distance. It's the sum of the coordinates. It's like walking down the blocks. One useful picture to draw is to think of the, let me draw this on the next page here, is to think of the distance from 0 where that distance reaches 1. Okay, so this would be the picture of a unit ball centered at the origin. Okay, so now the L2 distance, this is value 1, maybe higher. 1. Minus 1 and minus 1. So now the L2, and so if this is, so if A, so we're going to draw a picture with A equals the origin, is 0, 0. And so the L2 ball is just what you expect is a ball. Right, so this is, the distance is the straight line distance in any direction you go. It's a distance 1. So it hits the coordinate axes and so forth. What is going to be the picture for the L1 distance like? What does the unit ball correspond for the L1 distance?
Square.
So, well, it's kind of, it's like a rotated square. What is okay, so what is the distance from this point right here? So is it should be a distance 1 to go up to here, right? And a distance 1 to go here, right? Because I'm just moving in one coordinate, the other one moves 0. If it's a square, what's the distance to this point? 2. So if it was a square and it came up here, that's not a distance 1. So I have to move closer in, right? How far do I move in? So it's going to look like this. It's going to be a diamond or a rotated square. So it's a square if you kind of turn your head a little bit. So, the distance to here is going to be 2 plus 3, and this was, if you can see the grid lines on here, I can see the grid lines. Can you see them? Okay. No, it makes it look like I can draw straight things. So, but it's 5 grid cells, and in the printed out versions you see online, you see it's 5 here, and it's 3 plus 2. It turned out that was right on that line. Right, so it's also, if I go this way, it's the same. I can go in either direction. So those are both at distance 1. So this is for the L1 ball. Okay, let me do another one before we talk about the general LP balls. So L infinity distance. So if we look back at this formulation with P, what is this L infinity going to look like? So I'm taking the difference between a coordinate to the power infinity, or something very large, but then I'm taking it by 1 over infinity. What effect is that going to have? First, what's going to happen if I'm only in, I only have one coordinate, so my vector is only in one dimension. Let's say, instead of infinity, think of something really big, like 1,000, or really use your imagination and go all the way up to 1,001 or something. Right? What happens if I take something to the 1,001th power and then I take it to the 1 over 1,001 power?
So if it's one dimension, then it'll just be the same, wouldn't it?
Yeah, good. So it's still going to go through, it's somehow going to hit these, any of these things along the axes, right? It's going to hit at the same point here as it did before. So these points are going to be the same distance in basically any of these LP distances. But what's going to happen in between? What's going to happen if I have 2 values? Like one is at a distance 2. So let's say the first coordinate's at distance 2, the other one's at a distance 1. So I take, so if I do something like 2 to the power 1,000 plus 1 to the power 1,000 to 1 over 1,000. Right? So this is still 1. This is, and this is like enormous, right? Super huge. But then I'm going to take the 1 over 1,000 again, and this one will basically come back down. And this one is just going to be noise. And as 1,000 gets bigger and bigger, eventually this one doesn't mean anything at all. So instead of writing it as 1,000, we kind of write it in the limit case. So we'll say that D 1,000 A B is going to be the max of 1 to D of AI minus BI. So it's the maximum difference of any coordinate. Okay, so now if we draw this, if I draw this, the unit ball on this picture, what is this one going to look like? You said the answer already before. Square, right? Now we're getting the square. Right, so if my point is out here, one coordinate is a distance 1, the other one is a distance, or 5 cells, the other one is a distance 2 in the y coordinate, so that one doesn't matter, I only care about the furthest distance. So there I get the square. Okay, so now what's going to happen, but I define this generally for p, what's going to happen if I take p equals to 3? What's p equals, so this is the L infinity, what would something like p equals 3 look like?
Somewhere in between.
In between what?
In between L2 and L infinity.
Yeah, right, so it turns out it's going to always go through the same thing, but it's going to go in between L2 and L infinity. And these are going to sandwich each other, and if I drew them better, but you can kind of imagine. So this would be like the L3 ball. Okay, and if you had an L1.5 ball, it doesn't need to be an integer. You know, you could do, this could be the L, this would be L1.5. Right, it's going to fit somewhere inside of here as well. Right, so kind of cool, right? So why, if we have all these different LP values, they're all of these are going to be metrics. Why do we normally use L2? Why is L2 so popular? It's the straight line distance. What can you see from this? Well, if you remember what the L2 was supposed to look like originally, what was nice about L2 here?
It's that the real world uses L2 distance, but space uses L2 distance.
So space uses L2. So why does space use L2?
It's symmetric.
But all of these are metrics. Between L1 and L infinity, they're all metrics.
Because when only rotate it, any angle is still the same.
Ah, good. So any angle is the same. Space uses L2 because space does not have coordinates. If I change my coordinate system, if I change these black axes, and I'm not going to draw because the picture is cluttered enough already, I can change the coordinate system, and the L2 distance is going to stay the same. All the other ones are going to change. The L2 is a ball, so if I rotate it, it stays the same, like a steering wheel, right? But the L infinity distance is going to, the corners are going to move. And the L1 distance, the corners are going to move to align with the new axes. Where did these axes come from? Well, sometimes those axes mean something to them. There's you know, it's important to say the first coordinate is substantially, you know, there's a reason why the first coordinate is such and the second coordinate is something else. I don't want to mix them up. Right? And when you rotate, you're essentially combining together the various coordinates, and we'll talk about this more, how to think about this in a few weeks. But so the L2 is the only one that allows you to rotate your coordinate system and without changing the distance. Okay. Okay, let me try and define one more kind of common version. Let's try this color. It's not great. Let's do this. Say the L0 distance. And so there's a slight variance in how this is usually defined based on how it's normalized. But this is kind of related to the Hamming distance. So the L0 would be A, B, Okay, so this is supposed to be an indicator function, which is 1 if A is equal to B, and 0 otherwise. So basically, and so this will give me, it's basically counting the number of coordinates which are exactly the same. Okay? You can maybe want to normalize this by D. That's not uncommon to do. It's not necessarily required. It's that, you know, that will line it more with this picture, but it's different. But the one without this normalization works when your goal is to count the number of coordinates which are different. Okay, so we'll see in various problems later on. What we'll want to do is just measure the number of coordinates which are different. Actually, this is what we used once we had those mid-hash vectors. We were counting the number of different coordinates. That was approximating the Jaccard distance for us, right? Okay, so what happens when I start trying to draw this picture for p less than 1? What's going to start to happen? So I want to stay consistent and still go through these corner points. So I'm going to have to, so like p equals 1/2 is going to kind of look like this. So this is L 1/2. This is going to look something like this gray one. And so L0 is going to L0 is going to keep coming in until it's basically, it's along the coordinate axes. It's just essentially, it goes out if it has something non-zero. And in 2D, it's not really explaining what's going on so well here. It's kind of different, but but it's going to look very different and harder to work with because these shapes are not going to be convex anymore. And so we'll see some issues with this when we talk about compressed sensing later in class. Okay, so also one more nice thing about this picture. So this notation, when I was using, right, let's see this L1 notation. Why does that make sense? Okay, so when I do something like one, right, that's telling me the norm of a vector. That's what this kind of saying, right? So in the one norm of a vector is you add up all the absolute values of the coordinates. The L2 norm is you take all the coordinates squared and then you take the square root. Right, so what I'm doing is I'm actually taking those two vectors and I'm subtracting them and I'm getting a new vector. Right, and so then I can just take the norm of that vector. So that's why this is convenient to think about. Instead of thinking of A as 0 and then B as someplace out there at a distance of 1, you think of the difference between A and B. And then that becomes a vector. And if A is 0, that is just B. Right, but if A and B are different, this still tells me how the distance around a certain point looks like. Yeah, so good to keep in mind. We'll try and, it's a really useful picture. If you haven't thought before, it'll come and help various other intuition, various other aspects later in class. So when we talk about clustering, that'll all be dependent on our choice of distance. And so it'd be good to think about what are the distances doing, to think about what are the clusterings doing. Okay, so before I move on from these LP metrics, because there's a lot more interesting things, I want to say an important a warning that if I don't do this, then people will always use these incorrectly. And this is a warning that there's a big problem that I don't have a solution to. I just want to tell you that there's going to be a big problem. So use for vectors in RD where, I should probably say only, where all the coordinates have this same unit. So, or maybe they don't, if the coordinates are unitless, that's also fine. They need to have the same unit, right? So you often will think of something where I draw something like the height and the weight, and then I can plot various people, you know, in this picture, and then I can think of saying the distance between someone with this weight and this height to someone with this weight and this height. Well, it's the distance between those points. What's fundamentally wrong with that?
Just they're different units?
Yeah, right. So why is that a problem?
The height will dominate, but everything will based on height.
Yeah, well, it depends on what scale I use for height. Do I use, is this going to be in inches, or is this going to be in meters? Right? If I choose inches, then the height could be really big, right? If I choose meters, it's going to be between 1 and 2 probably, right? But if I choose inches, it's going to be, you know, greater than 60 usually, right? So where if I choose weights, similar. Do I measure in pounds? Do I measure in stones? You know, they're all, what's the metric? You know, in kilos, right? In tons. If I change those units, it scales the importance of different coordinates. Okay, so if I don't have the same coordinates, then how do I measure the distance? So there's a common thing people do is they will normalize. Okay, so they will normalize, and there are two common ways that they normalize. One is so all chords fall between 0 and 1. So they all fall between 0 and 1. So you find the smallest one and you subtract that from everything, and then you divide by the largest one remaining, and this gets you between 0 and 1. The other thing is they say that they have a mean equal to 0 and the variance equal to 1. So they basically subtract the mean from everything, and then they'll divide through by the standard deviation, and this will give us like this. Okay, so this is a common way to solve these things. Both of these are hacks. Okay, sometimes they will work, but they can have issues. For this one, if you make all the coordinates between 0 and 1, if you have a single outlier point, it's going to completely change your coordinates, the weight of that parameter. Right? So if you have a single point on the outlier, if all my coordinates were between, say, 0 and 100, then I would just scale by 100. But if I had one and I had 1,000,000 points, but one point was off at 200, then they all become between 0 and 0.5 because of one data point, and maybe that data point was noise. Right? And so with the mean and the variance, well, so it's, you know, what's going to happen is you're going to potentially, it's going to work differently than this one, but why is this one better? You could have some points very far out, but some points might be very close. So it's going to be more robust a little bit, but it's still not perfect. There's no, you know, it could be that one coordinate is more important than the other ones. Both of these are saying all coordinates are roughly equally important, right? Maybe, you know, I think that Height is much more important than weight. I don't know, right? And even if you put them in inches and pounds. But I think height is much more important, so I'd really want it to be 7 inches instead. Maybe that's a better way of measuring distance. Sure, that's possible. It's, neither of these is always right or always wrong. But you shouldn't blindly just do this and assume everything will be okay. And you shouldn't blindly just use it with some units. Both of these, by the way, because they're dividing by at some point, they're dividing by either the standard deviation or by the largest value. They're getting rid of the units, so that's good. But maybe they weren't getting rid of the units in the right way, in a meaningful way. So you can maybe do this, but be careful what the consequences are. So we'll see in class later that some techniques we do will rely on some distance, and you may have a bunch of varying attributes, height, weight, various other things. How do you combine them is not necessarily obvious. There's some stuff you can do with the family. One possible solution is what's called distance. One possible solution is called distance metric learning, and basically it tries to find a normalization or scaling of these so it's so that you do have a distance, and you need to have some input. You need to say certain things are far and certain things are close with some values. You don't have to label everything, but if you have some labels, then you can try and learn a metric that applies for everything. And this will be related to a technique that will multidimensional scaling that we'll talk about in the PCA SED lecture. Okay, but there you need to have some labeled data. Some things are further than others, and you have some numerical quantities associated with that. And if you're not careful, that can add bias, because you think, oh, these nests really should be far apart, and these shouldn't. And maybe that works, maybe it doesn't. But this is kind of an issue. And so often the distance metric learning will take arbitrary things that you can measure some way and map them into a lower dimensional Euclidean space, often the L2 distance. So back to the LP distances again. But there, the units will hopefully be taken care of in a way that at least makes sense to your input. Okay? All right, so that's say about LP distances. Let's talk about some other distances. So one thing we talked about before was the Jaccard distance, right? Where this was just 1 minus the Jaccard similarity between two sets, right? This is again a distance, but it's not between two vectors. This is in between two sets. 1 minus A intersection B, A union B, and this one is also going to be a metric. So you can define metrics not between things other than vectors. Right? Let's quickly go through the properties. The similarity was between 0 and 1, and we did 1 minus the similarity, so this must be in 0 and 1, so it must be larger than 0. Okay, so it satisfies M1. M2 was, I think, symmetry. No, M2 was, let's check what we said. M2 was 0 if and only equals 0. So, okay, so 0, it's only 0 if these are the same. That means that the Jaccard similarity, this, should only be 1 if they're exactly the same. And that means the intersection is equal to the union. That's only true if their A is exactly equal to B. Otherwise, the union has some other stuff in it, right? So the symmetry holds because intersection and union are both symmetric operations on sets. And then the triangle inequality. I'll give it's not too hard to see. So you want to say, so let's do a short proof of the triangle inequality. Okay, so we're going to pick so another set C, and so what we want to show is that the Jaccard distance, do the Jaccard between A and B is less than or equal to the Jaccard of AC plus the Jaccard of CB. Okay? So there are two cases to consider. So if C is not in the intersection of both A and B, remember that we have A and B is the two sets. If C lies out here or has some parts that don't intersect, you can always make it smaller. You can always make the distance to these things smaller by moving it closer to the intersection, right? So if it partially intersected, if part of it intersected here, you can always make it smaller by getting rid of the stuff non-intersection. Hopefully that's easy to see. So this side only gets smaller if you make it more in the intersection. So let's assume that, so the interesting case is when C is a subset of A and C is also a subset of B, or that means C is a subset of A intersection B. So that means now we'll say that the set C is going to lie inside of here. It's somewhere in the intersection. If it was somewhere out of the intersection, it would only, any part out of it would only make this part larger. So it would still hold. Okay? So let's assume it's in the intersection. So that means that we can write the Jaccard distance, this side is going to be equal to A set minus C over A, because the size of A. This is because the union of A and C is just A, and the symmetric difference, which is going to be 1 minus the intersection is the symmetric difference, is just going to be the part of A not in C. And this is going to be similarly B set minus C over the size of B. And this is going to be greater or equal to A set minus C plus B set minus C divided by A union B. So this one should be larger because I'm dividing by a larger quantity, both parts here. So that means dividing by a larger quantity, this is smaller. And so then I can also say that this is going to be larger than asymmetric difference B. Remember, asymmetric difference B is this part here. Over A union B, and this is exactly equal to the Jaccard distance between A and B. Okay, so I proved, this is the proof. Right, so the asymmetric difference B is exactly 1 minus, or if I divide through by the union, is the part in the numerator if I have this as a single fraction. So this is exactly equal to the Jaccard distance. Okay, so it satisfies the triangle inequality. So that means that this distance, the set also satisfies this metric property, and so there'll be algorithms, there'll be some clustering algorithms we need that need to use a metric. That means you can do clustering on Jaccard distance instead of on sets, instead of on vectors, which will be kind of the intuitive way to think about Could that make sense? Okay. All right, so let's talk about a different distance called the cosine distance. And so this it'll be useful to draw the origin here. And so then I'm going to have two vectors, A and B. Now I'll think of them as actually vectors from the origin. And then the cosine distance is going to be cosine of theta, where theta is the angle in between those vectors. Okay, that seems kind of strange. I don't want to, now I have to compute an angle between vectors. How do I do that? Turns out that you can do this with some dot products. This is the equivalent to the dot product, 1 minus the dot product between A and B over the norm of A times the norm of B. Or 1 minus this, and remember the dot product is AI times BI, and then times the norm of A. So the dot product is just the sum of all the coordinates multiplied together. Right, so now this cosine distance is, this calculates the cosine of that angle. Your cosines and dot products are strongly related. Okay, so this is a very, yeah.
Is that the L2 norm?
No, it's not quite the L2 norm.
Of the A and B on the bottom? Sorry.
Yeah, so those are, yeah, great. If I leave off the 2, it's, if I leave off P, it's the 2. The 2 is the default value. Good question. Yeah, when you're talking about angles, I don't want to have to think about coordinates, so I'm using the L2. Okay, so the cosine distance is heavily used when I'm words data. So the bag of words is a different way of turning a document into some object we can take the distance between. So the bag of words is where I take some document and I keep track of the number of words of each type, right? So if I had, this is for if I have the phrase up and up, so then maybe this is the vector where this is the word the, this is the word and, this is up, and this is it, right? You can think of it keeps going. It can be a really high dimensional vector, right? But in this phrase, up and up occurred twice, and occurred once, the occurred 0 times, it, or maybe that's if, depends on how you like my writing, is a 0. In fact, they're both zeros. There's a whole bunch of other words which are zeros. But I've turned this document, now this is different than k-grams, and then I'm not modeling as a set. I care about the quantity now instead. Up occurred twice, that's actually significant, instead of, if I just said and up, that probably means something different than up and up. I don't know. They probably convey roughly the same emotion. Okay, so when you're using bag of words models, you often use this. Note that to compute this distance, I can do it faster than actually looking at all the zeros. I just need to look at all the non-zeros. Because when I'm taking this sum here, the dot product here, or even these norms, right? The norm, I just add up the square of all of these, of all of the coordinates that are non-zero. The zeros don't affect it. And the sum there of all the coordinates, if one of the thing has a 0, if either of them has a 0, that coordinate overall gets a 0. So I only care about for the coordinates that they both have something. So for words that are not occurring, I don't need to use those in the distance calculation. And this is really useful. So again, like the min-hashing, it didn't depend on what words were not in the set. Okay, and so when you're using bag of words, this is a fairly common way to measure the distance between these vectors. Okay, so is this one also going to be a metric? Okay, well, let's go through. So M1 is orange. Let me switch colors. M1 was the property that it always had to be greater than 0. Yes, so the maybe I'm supposed to normalize that or take the absolute value of the. Yeah, so all of the counts are greater than 0, right? These values, I'm assuming I input are greater than 0, but if they're not, you can enforce the absolute value. You can use the absolute value of the inner product instead of getting some value that's negative. If you really want the cosine, you should do that, right? So I can take the absolute value here. And because I'm I'm dividing by the norms, it'll ensure that the part you're subtracting from 1 is going to be at most 1. So this means it's going to go to R plus. Okay, so M2, let's come back to M2. Let's say M3. M3 was if this was symmetric. Right? The distance should be the same from A to B as it was from B to A. And all the operations I do are symmetric between A and B. Right? Let's look at M2. M2 was, that was D cosine AB equals 0 if and only if A equals B. Is this true? How can I see if this is true? Thoughts? No?
Isn't that not true?
Yeah, it's not true. How come? Where would it not be true?
He's a scale, like a scale version of A.
Yeah, right. So I have two vectors. Let's say that A is equal to 1, 0, 0, and B is equal to 2, 0, 0. Right? These are going to have A and B in this case, where B is exactly a multiplicative factor of A. These are going to have a cosine distance of 0. So I'm only taking the angle, right? If B was instead up here, the angle between A and B is 0. Right? So the cosine of the angle is also going to be is also going to be 0. So this is not a metric. Okay, so why would you want to use this if it's not a metric? Let's think back to this bag of words model, right? Bag of words model of a document. It gives me a vector with the word counts, and then I want to compare the vectors from it. Why? And so let's say I had two documents that had so let's not worry about them being exactly 0, but let's say there's two documents where one is much longer than the other, but they're about the same topic. They have the same words in them, and roughly the same counts of words, except one just has more of those words. Right? Those documents should still be similar in terms of what topic that they're on. So people are often trying to look at these documents, and these bag of words model or these K-gram models are trying to say, something about the topic of those documents. What is the kind of, if things are similar, they should be talking about similar concepts, maybe in a similar way in some ways. And so if they're using the same words, there's just more of one than the other, then they should still be considered fairly similar. So I want to normalize out the scale. So, and that's what this normalization part here is doing, right? This is, so normalizing. So this is normalizing the data so that I don't care about the magnitude. The magnitude of the vectors don't matter anymore, just kind of which set of words direction are they pointing in, right? Okay, so it's not a metric, but it's still very useful. If you look at the M4 property, if instead of these vectors, you think of the normalized versions of these vectors. So you convert A into A prime equals A over its, and this equal to B prime. Right? So if I convert these into these vectors which are normalized, I took the word counts and I divided by the L2 norm of these vectors, then these will be, then all of these words will be unit vectors. And in that case, it's going to satisfy this M2 property after I've normalized the vectors. They're only going to be the same if they point the same direction.
If you normalize them, don't they turn into, could they then be interpreted as probability vectors?
Almost. The things don't sum up to 1. If you normalize by the L1 norm, that's going to be the case.
Okay.
They're going to lie on the unit simplex instead of on the a part of the quadrant of the unit sphere, if that makes sense. So if you look back at this picture, after I've normalized them, they're going to essentially lie on the L2 ball, when if they lied on the L1 ball, then they would be probability distributions. But that's a good insight. It's often cool to model things as probability distributions. You can take these bag of word vectors and then normalize them by the L1 norm, and then it's like the probability that a certain word is being used. And that's a cool way to think about it. It's not what the cosine distance is, but that's a perfectly reasonable thing to do as well. And then you can look at the distance, say the Euclidean distance between those vectors. Actually the next thing I'll talk about that's the right way to pre-process the data. Okay. So I'll get back to that. Okay, so does it satisfy the triangle inequality? So the way to see it is after you've normalized, you can see that this is true. And again, this rationale is what I was just saying. It's going to lie. All the data points are going to lie on this L2 ball. And so I'm going to have 2 points here, say A and B. And so this angle between them, right, instead of thinking about the cosine of an angle, I can think of it in terms of the radians. And that's its monotonic relation with the radians. It's going to have the right, monotonic is enough. You can think of it as the radians, which is the length of distance on the L2 ball. Do you ever remember what radians are from your geometry class? It's the geodesic distance on the L2 ball, and that will be I forget what it's proportional or what to the cosine distance, but that is going to satisfy the triangle inequality because it's the geodesic distance on a metric. And there's a more straightforward way to show that, but I'd rather talk about this next distance instead. So once you normalize, it becomes this nice metric, but it has that normalization baked into the calculation, so it's not a metric as typically stated. And so if you just have those word count vectors, it's not a metric between those. Okay, so the last main thing I want to make sure to cover is the KL divergence. And so this is a divergence, which is this is a type of distance, but there's a class of these divergences. There's other divergences other than the KL. KL stands for the Kullback-Leibler Kullback-Leibler divergence. There's other things. I won't list them out, but they will have similar properties to KL divergences, and this one also is not going to be a metric, and they'll be more pretty easy to see. You're going to apply these to probability distributions. So instead of A and B, let's add P and Q, which are, let's say, which are discrete often, and there are continuous versions of this as well, but I'll write discrete versions. So probability distribution, and so that means that for P is going to be equal, again, it's going to be a vector in RD, but such that Pi is going to be greater or equal than 0, and the sum over I equals 1 to D of Pi is going to be equal to 1. Right, so it tells me essentially, think of it like the bag of words after I normalize by the L1, then it says the probability of a certain word if there are D possible words. Okay, and now the KL divergence. So it's often written as, instead of a comma, where you usually write a distance, it has this double bar in between them. And the reason for that will become clear in a second. It's going to be equal to the sum plus I1 to D of Pi times then the natural log of Pi over Qi. What is this strange object? Well, the first thing you should notice is that this is not symmetric in P and Q. And that's why they don't write it with the comma, I guess, just to remind you that it's the divergence from P onto Q. So when you think of these as probabilities, this should look kind of like the entropy. In fact, if you're familiar with entropy and cross entropy and stuff, that this is the cross entropy minus the entropy of P. So if you're familiar with that information theory, you can cover it that way. So there's, with all of these divergences, there's some form of underlying parabola that you work with, and essentially, if this is P and this is Q, that it's basically, if I draw, let me try and draw this again. If I draw a tangent plane at P, then it's the height at the value Q. And so all divergences have this sort of property, and you can see by going back the other direction that this would be very, if I drew this better, it could be much larger going the other way, one way than the other, based on the slope of the parabola is usually the further out you go. So from something more extreme, and in the parabola, something more extreme would be that it has more measure concentrated in a small number of coordinates. The distance from that to something else would be much larger than the other way around. So I'm not going to go into try and flesh out all the idea what's going on here, but this is roughly the way to think about this is the amount of information in an entropy sense of information you have to change from P in order to get to Q. So if you think of there's some, if you're in one of these, if you're in do signal processing, you could think of there's some sort of channel, and that you want to send information with bits across, and you think the other party already has the value p, and you want to tell them the value q, so you need to tell them the difference in information. And that's what this Kale divergence is capturing. And it turns out it's different going from they know p to tell them q than they know q to go to p. And so if q is much more concentrated around a small number of values, it takes a lot more information to fill in the rest of the information, it turns out. Okay, so this is often what is used as a distance between probability distributions, because it's really capturing the amount of information between them. So this is very common to use. So if you were to model your bag of words as a probability distribution instead of as these normalized length 1 vectors, then this would be a very common distance. But again, it doesn't satisfy the triangle inequality, so this is going to not be suitable, at least immediately, for a lot of the algorithms we talk about. There are often ways to make it work, but it's kind of more painful to be careful about it. But this models something kind of that aligns better with this idea of it being a probability distribution than just the Euclidean distance or the cosine distance. And let me draw another picture of a probability distribution. So one way to think of this probability distribution I was mentioning is this L1 simplex. So by simplex, I mean, let me try and draw this in 3D in 2 pictures. So all the coordinates are positive, and say that this is the x, y, and the z axes. Then the simplex is the thing that goes through these at a distance 1 from the origin everywhere. And what you end up getting is this triangle that lives in 3-dimensional space, but there are only 2 parameters which are free. Okay, and so if I map this, and then I can draw this now in the plane, and it's going to look like an equilateral triangle with the x, y, and z axes. And if you have more than 3 d minus 1-dimensional subspace, and then it becomes an equal-sided thing in with d corners that's going to lie in d minus 1-dimensional space. But any probability distribution is now going to live inside of here, right? So something that has probability 1 of being y and 0 of x and z is going to be right here, and vice versa. If it's equally likely, all of them, it's going to be in the middle. If it's over here, it's going to be more y than x or z. If it's here, it's not going to have any probability of being x, but it's somewhere between y and z. It turns out any point inside of a triangle, this is kind of a cool thing. So this point P here can be written as, let's say, A here, can be written as the sum, let's write them coordinates from 1 to d as EI. So EI is going to be equal to the unit vector in the ith axis, in the ith axis. So this is, the ith coordinate is 1, the rest are zeros. So for instance, this is I1, I2, and I3. So it's 1, 0, 0, 1, 0, 1, 0, and 0, 0, 1. Right? And so this, anything can be written as a linear combination of these vectors. A convex combination, that means that these sum up to 1 and are all positive, will lie in this triangle. And this will be all probability distributions. And then it turns out that kind of the right way to measure information about these probability distributions is with this Kale divergence. Now it's not the Euclidean distance in here. You could use that as well, and some people do. But it's gonna say that these things are kind of harder to get to in the corners than they would be otherwise, is essentially what it's saying. It's kind of a cool way to think about it. This is I promised some high-dimensional geometry. This is a little bit here. I've run out of time. There are a couple of more useful distances that we maybe are worth knowing in the notes. One is the edit distance, which is a notion of distance between strings. It's the number of it's the number of characters you need to change to get from one string to the other. This is useful for very small snippets of text. Like if you're doing keyword searching in Google, it will do a spell check based on something close in the edit distance. And it may weight different substitutions as being more likely based on maybe where they are on the keyboard, typos, or they sound similar. But it's basically the number of things you need to change. And the graph distance is something we'll talk about later. It's basically the number of hops you need to go on a graph, and that's also a metric. Both edit distance and graph distance are useful metrics for other scenarios that we'll talk about. Okay, so Wednesday we'll talk about other ways to solve these similarity problems that don't need you to be as high dimensional as LSH. They work in these what I call low and medium dimensions and are very useful, but can scale up to say 100 dimensions in some cases. All right, and then we'll move on to clustering next week. So, all right, class dismissed.